Hi, everybody. So there were a couple of questions on this last one in section 1310. And this was number 7 in the homework. It was the last one. And the question is to use Lagrange multipliers to find the dimensions of a right circular cylinder with volume V0, cubic units, and a minimum surface area. Okay, so here's my little crude cylinder. So we know the volume of a cylinder, V. Let me try that again. All right. Yeah, so the volume of a cylinder is just pi r squared h. And in this case, this is given in the problem. It's just V0, whatever that is, right? And so this is a constant. So the volume is fixed. And what we want to minimize is the surface area. So the surface area of a cylinder, well, you have the sides of the cylinder. This part here is just 2 pi RH. And then I'm assuming that this includes the lid, which is the top of the cylinder. And that's just a circle of radius r. So that's pi r squared. And then the bottom, the floor, is also pi r squared. So we have 2 pi r squared. Right? One for the top and one for the bottom here. Okay, so that's the total surface area. Right? And this is what we want to minimize. Okay. So yes, this can be done by substitution, but they want us to use Lagrange multipliers. Right. So yeah, this could have been done in Calc 1, but we're going to do it in Calc 3 here. So, right, so the objective function, the function that we're trying to minimize, is area. So I will write that. Oops, sorry, wrong color. I haven't done this in a while. So area as a function of r and h, right? So this is usually our f, right? And it's just this function, right? 2 pi rh plus 2 pi r squared. Okay. So the constraint function, which I'll still call g, and it's still a function of r and h. Right, that's the volume, and it's just pi r squared h, which is given as V0. Okay. Right, so Lagrange multipliers, the Lagrange equation is the gradient of f is equal to some constant lambda times the gradient of g. Just keep in mind that here I'm not using f, I'm using a for area. These are vectors, so I'll put little arrows over them. Right. So how do we find the gradient? We just have to find both partial derivatives. Right. So the gradient of a is just the vector partial of a with respect to r times I plus partial of a with respect to h times j. Okay. So with respect to r, we get 2 pi h plus 4 pi r. And that's all times I. That's the first component. And then the partial with respect to h, so that's just 2 pi r. Right. It might help if I just write it in brackets here with a comma. Right. So that's the gradient of a. And then the gradient of g. Right. So that's going to be, using the angled bracket, partial of g with respect to r, and then partial of g with respect to h. So with respect to r, remember here's g now. It's just pi r squared h. So with respect to r, you just get 2 pi rh. And then the partial with respect to h is just pi r squared. Okay, so those are the gradients. So now we can think of the Lagrange equation here just in terms of the partial derivatives. So the partial of a with respect to x is going to be lambda times the partial of g with respect to x. And then do the same thing with respect to y. So the first equation with respect to, oh, I'm sorry, we're not using x, right? We're using r. There's no x and y here. It's been replaced with r and h. Right? So it's not f of x, y. All right, so with respect to r, right, it's going to be this times lambda, this equals lambda times this. So let's try that again, right? Partial of a with respect to r is going to be lambda times partial of g with respect to r. So that's 2 pi h plus 4 pi r is equal to lambda times 2 pi rh. So that's the first equation. And then the second is with respect to h, both partial derivatives in terms of h. So those are the second components. You just get 2 pi r equals lambda times pi r squared. Okay. Right. Now remember, we have three variables here. The variables are r, h, and lambda. But these are only two equations. The third equation is the constraint equation. Right? So the third equation is just pi r squared h equals v0. Okay. So we just have to solve these equations here. And I'm going to start with the second one because that looks easier to me. Right? All we have to do is divide by pi. In fact, we can also divide by r. And if we do that, we just get 2 equals lambda r. Right? So lambda r is equal to 2. Or, depending on what you're solving for, right, lambda is just 2 over r. Or r is 2 over lambda. Right. So now let's go back to the first equation, which is a little bit harder here. So I'll write that down here. So 2 pi h plus 4 pi r is equal to lambda times 2 pi r h. Right, so first thing I notice is that we can factor out a 2 pi here. So that's 2 pi times h plus 2r equals lambda times 2 pi times rh. Right. So here we can divide by the 2 pi on both sides. And now we have the equation h plus 2r equals lambda r h. Okay, and the other equation we had was 2 equals lambda r. Okay, so again, it's just a little bit of algebra, but I think you should be able to solve this here's the slick way of doing it, right? Where do we see lambda r? Here's lambda r, right? So that's just equal to 2. Okay, so I can substitute for lambda r here, lambda times r, that's just 2. So h plus 2r is equal to 2h. Right? Subtract h from both sides, and you get h is equal to 2r. Okay? Okay. So yeah, so essentially the height is just twice the radius. If you go back to the cylinder up here, right? If the radius is, 3 centimeters, the height is twice that. It would be 6 centimeters. So I drew it pretty well here, not knowing the answer ahead of time, so I lucked out, I guess. Okay, so keep in mind, what are they looking for here? They're looking for r as a function of v0 and h as a function of v0. So remember what v0 is, right? It's pi r squared h. So yeah, if the height is 2 times r, I can replace h, right, with 2r. Right? So h is just equal to 2r. And now that gives me 2 times pi times r cubed, right? R squared times r is r cubed, equals v0. And I can solve for r. This is supposed to be an r here. Let's try that again. Yeah, so 2 pi r cubed equals v0. So solving for r, just divide by 2 pi. And r cubed is v0 over 2 pi. So to find r, just take the cube root. Okay. So in fact, that's the first answer here, right? R as a function of v0 is the cube root of v0 over 2 pi. And if you're having trouble in WebAssign with the cube root function, they would accept this as, in parentheses, v0 over 2 pi to the power 1 over 3. So that's how you can get around searching for the cube root function. But it should accept it either way. Okay. Now, they're also looking for h as a function of v0. But remember what h is. H is just 2 times r. And we know what r is, right? So this is just 2 times r of v0. So just multiply the whole thing by 2. This is 2 times, in parentheses, v0 over 2 pi to the 1/3. And believe it or not, they accepted that too. If you simplify this, you can also write this as, I think, 4v0 over pi all to the 1/3. Again, I think WebAssign is getting pretty good at accepting equivalent forms here. So it should accept either. If not, well then, just put it in the form they like. But of course, I would accept either as well. So, right, so there you go. Right, so r of v0 is just the cube root of v0 divided by 2 pi, and h of v0 is the cube root of 4v0 divided by pi. It's probably clearer down here. Okay, so that's using Lagrange multipliers, right? And yes, it probably would have been easier by substitution, right? In other words, in Calc 1, you would solve, say for h here, you would write h as v0 over pi r squared, and then plug that in for h, and then you'd have area only as a function of r. Right? So to minimize that, you just need the ordinary derivative, right? And then set it equal to 0 to find the critical numbers and all that stuff, right? So there's one other thing here, right? Lagrange multipliers, remember, only finds the optimum answer. How do we know it's a minimum and not a maximum area? Well, to do that, you can use the second derivative test, but let's not bother. Let's just assume that it's not a trick question here. So when they say find the minimum surface area, that that this gives you the minimum surface area and not the maximum. I think that's a fair assumption. Right? There's no trick questions here, or there shouldn't be. All right, so I hope that helps.